the PWM modulator. This is a compensator. And we are going to have the T flat. And here is the VO. Is the control loop. Now, before getting to the detailed design of the closed loop control, first we need to figure out what is this one. Here we are going to have an error signal, right? This error signal is going to come to this transfer function, whatever it is, we're going to talk about it. So this transfer function, I think I made a mistake. Here I said D, but this is basically V control. The V control coming here, output of this one is a D. Duty cycle, going to the plant, right? Because this plant basically is going to be your buck converter or boost converter or buck boost converter, whatever you have. There's the one switch. You need to tell that switch with what duty cycle to turn on and turn off, right? Now let's think about this. Let's think about this PWM here. PWM modulator or mechanism. There's a control signal coming here. We need to translate that one. We need to change that control signal to the on and off signals, right? Like what we did for the three-phase inverter. We had an MA, MB, MC coming in. We compared it with a triangular waveform, right? And we say if it's more than that, it's on. If it's less than that, it's off, right? And we went through the equation for that. Here we select a simpler, sawtooth here, for here. Basically, a V control is going to come in. V control is going to come in. Compare with a sawtooth. You can select the same thing we had before, but this is easier. Right? So you have a sawtooth. The frequency of this one could be 20 kilohertz, 10 kilohertz, 100 kilohertz. This is the high frequency, like the PWM signal we had, right? The triangular with the frequency was like 10 kilohertz, 6 kilohertz, whatever. So this one is the one has a high frequency. Now let's look at it here. Let me put it here. So basically, if we look at it here, let's say this is a sawtooth. I'm going to exaggerate it here. So let's say we had a V control. For now, I'm going to just do this part. This is a V control, right? This is a V control, and let's say the peak value of this one is the VP, right? Let's say the peak value is VP. First of all, let's see how the DT is going to look like. If we look at the DT, how is it going to be? If V control is more than the triangular waveform, the switch is on, and if it's less than that, it's off, right? Basically, let's keep it here. So, and this one is going to be on, one means on, right? Or off. Let's find out what's the relation between this and this. So this is a D, right? This is the DT cycle, right? How much? This is DT, this is T, right? T is the switching frequency of 1 over switching frequency of the converter, right? Now, let's look at this triangular. let's call it A, B, C, D, E. So we know triangular ABC is similar to triangular ADE, right? Because this one is parallel with this one, right? So I can say AD over DE is equal to BC over, sorry, I made a mistake. AB over AD, this is AD, is equal to BC over D, right? Let's replace them. How much is the AD? How much is the AD? Is VP minus V control, right? So it's going to be VP minus V control divided by. How much is the AD? VP, right? How much is the BC? 1 minus DT, right? So this one is a 1 minus DT. I call this one DT because if you change it, it's going to change, right? It's not a fixed value, you know, based on the control system, how much is calculating it, it's going to change. So how much is the DE? T. Let's get rid of these two, right? So it's going to be, divide this one, it's going to be 1 minus V control over VP is equal to 1 minus VP. That's this one minus control T, V con T. This is again, the control signal can change anytime, right? Take this one T. So this one is going to be like this. So basically we're going to have 1 over VP this is a transfer function of a PWM generator, right? This is a transfer function of the PWM generator. So basically here, whatever is coming here, right? I should time it by what? 1 over VP, right? And this is the DT. So DT is going to tell you the percentage of the time this one should be on, right? If D is going to be a number between 0 to 1, right? If D is 0.7, means you should have a 70% duty cycle, right? If D is, I don't know, whatever, if 0.8 means 80%, 0.2 means 20%, right? Now, again, this is the real signal. But if you remember, we calculated transfer function based on a small signal, right? Or linearized model of this one. Let's do the same thing here. We said, okay, so again, the V control T can be V con, a value, maybe this one, maybe this V control would be like this. How many of you have seen this one right now? In your inverter you are doing. Anybody finished, has learned anything with the control system of the inverter? No, you can look at flyback off, but what phase 3 of the project?
Still working on that.
Huh?
Working on that.
Okay, working on that. Yeah, and when I finish this one, remind me, I need to talk about something to you about the final project. So, if you look at that one, just I'm telling you, if you do a very good job and you do the control correctly, if you look at the MA, MB, MC, you are going to see something like this. This is the MA, but actually, based on what you have, you are going to see something like this, not that one. That one is a sine wave. You're going to see something like this. If you do the right, if you have a good result. If you have a bad result, I don't know what you're going to say. Maybe your system is not working, I don't know what you're going to see. But, again here, we can say, but for a DC to DC converter is different. The values are DC. This is the AC system, right? For a DC to DC converter, we have something like this, and it's going to be like this, right? So I said we control, let's write it, the DC value plus V tilde control, right? And we know from the previous one, dt was dt, d plus d tilde, right? So let's replace it in this transfer function. Let's replace it in this. So d plus d tilde over v con plus y, then put the vp plus vp tilde. Why? I can put a vp plus vp tilde, right? This is what I'm going to generate. This is a south to some. That is not going to change. This is fixed, right? So now if you do a little bit calculation here, so it's going to be then d plus d tilde is going to be, just I want to write it down. Let's say this one also you can say dt is v con over vp, right? That's another. Just now let's time this one. It's going to be v con over vp plus v tilde con over vp, right? This one and this one, they're gonna cancel each other, right? That's the steady state answer. See, that's the equation here, right? V dc con over vp is the dc value of the d, right? Right? So basically, the transfer function for the small signal is not different from the general transfer function we have, right? That's the same thing. That's the same. So basically, if I replace this one, for example, for the, I don't know, buck or boost converter, the transfer function I found here, so here I should replace this one with what? 1 over Vp, right? This one is very simple. It's going to be 1 over Vp, right? Now, I'm going to talk about this one. I'm going to talk about this one. That's a error compensator or error amplifier. They call it error amplifier on the DC to DC converters, or we call it compensator or controller, whatever we want to call it. We can call it. Now, before going there, I want to define, for some of you maybe reminding you, or for some of you maybe the first time you're seeing it, I don't know. Let's go over it now. Before we start to talk about this one, I want to talk a little bit about the Bode plot, phase margin, and those kind of things, because we are going to use that one a lot, from now, Let's see, what is the Bode plot first? How many of you don't know what the Bode plot? Oh, that's good. Everybody knows that, huh? You have heard that one. That's great. That's great. So, but I'm going to quickly review it again. Let's see, for example, I'm going to go with a very, very simple example. Very, very simple example. If we have a transfer function like HS, for example, right? This is a review of Bode plot. If we have a system has a transfer function of HS, right? So if you change S to omega, right? We say J omega, right? So this is the complex number, right? So this one is going to have a magnitude and it's going to have the phase, right? So the phase, they call it phase. That's the phase of this system. But usually for the magnitude, you can go with directly this one one, they go with the logarithmic, right? They go with the 20 logarithmic of this thing, right? They take 20 logarithmic of this one to calculate. So usually they use this one. Instead of using that one, they use this one, right? This is what they use. Now let's see a very, very simple example. If we have a, for example, h of s, I'm going to go with a very simple one. Is 1 over, for example, 2 plus s. Right? This is very simple, transfer function. So what is the h of j omega? Is going to be one plus 2 plus j omega, right? How much is the phase of j omega? How much is this phase?
It's tangent inverse omega over 2.
Basically, it's the phase of the denominator, right? How much is it? It's 0 minus phase of this one. How much is the phase of this one? Is the arctan omega over 2, right? So basically, because the phase of denominator is 0, it's going to be minus right? That's the phase of this one. And how about the so basically this one is going to be 1 over right? But this one is going to be right? Usually if you are going to plot this thing, how do you plot it? We go here, say. This is a very simple system, You go find it point by point, right? Or you go by minus 2 dB, given a dB at those kind of, it's a minus 20 dB, right? This one is clear, it's a minus 20 dB. But you say if omega is 0, how much is the gain? The square root of 4 plus omega 2. If omega is infinity, it's going to be infinity, right? Log of infinity is infinity, right? So but it's going to be time minus 20, it's going to be minus infinity, right? Basically, this one is going to be like, if you put it in the logarithmic axis, it's going to be like this. You're going to start from here, you go like this, right? It's going to go logarithmic axis, I'm saying, it's going to be linear, right? Now, if you look at the, this is a zero gain, right? This is a low DC gain. We call it DC. Why we call it DC gain here? Whatever value is here. Yeah, because omega is 0. That's the low frequency gain, right? Because I'm going to use this term later. Low frequency gain, right? And here is the high frequency gain, right? So, how about the phase? How much is the phase? So it's going to start, let's put again omega 0. How much, if omega is 0, how much is the phase? 0, right? Our tan of 0 is 0. 0 to the minus here. But if omega goes to the infinity, minus 90. It's going to go somehow, something like this to minus 90, right? And this is the omega axis. You guys, you should know these things from courses, but one of the control courses, Yeah, we call it Bode Plots, right? Phase and gain. Now, let me put this here. What is the phase margin? What is the phase margin? That's something else I want to look at it, you know. Let's say, so let's forget this example. So now we know what's a gain. This is 20 log, right? So, which the axis is going to be decimal, right? They call the unit, they call it decimal. Let's say, we're going to see what's the definition of phase margin. And anybody, anybody can remember what's the phase margin?
The difference between the phase and 100 minus 180 degrees when the magnitude is
When this one is 0, right? Let's say if we have a, can everybody was, I'm going to put it here. If this is a, I put 8k omega, but I mean 20, that's a logarithm. Let's say we have, I don't know, a transfer function is like this, for example, right? Let's say h of j omega is like this. Basically, this one has a one pole. Pole is the roots of the denominator, right? And here, one pole, 1 0, because it becomes flat, right? So there was a 1 0 to cancel this one. And again, there is another pole here, right? We call this one omega cross, or crossover frequency. So basically at omega cross, how much is the hj omega? Is 0, right? I mean 20 logarithm of hj omega. So let's say the phase margin, for example, is like this. The phase of the h is like this. I use this one because this is exactly what we're going to have later. Let's say we had a function. We had a transfer function. It had a phase margin like this. This is a minus 90, and this is 0. So basically, to find the phase margin, we'll go find out where this one is 0. At this point, we'll go find the phase of h omega, right? So phase margin will be defined. Phase margin is defined as 180 plus and this one is in negative, because you know you can plot this one to be negative or positive, but this one is negative. This is the phase margin, right? We'll go find out when absolute value of the h omega is 0. At that frequency, we'll go find the phase. 180 minus that is going to be the phase margin. Now, for a system, so what's the definition why we are using this one? I'm not going to get to the detailed control theory, but for a system, closed loop system, if the open loop system transfer function had a phase margin of 45 to 60 degrees, this is a very good number, 45 to 60 degrees. This is the goal for us. That system is pretty stable. We're going to use this one later. If we have, we can design the system. See, this one is not under my control, right? Because this is whatever RLC you saw, the equation. Whatever is in the box is going to be there, right? I cannot change this one. This one is the simple, this is 1 over VP. That's whatever is the peak of this one, right? I cannot change this one. But here is under my control, right? I want to design this system to have a phase margin of something between 45 to 60 degrees. So now my system is going to be pretty stable. You can go look at, those ones, they know a little bit more about control. When we calculate this thing, you can go plot the root locus of the system to see where we are. I'm not sure how many of you are familiar with the root locus. How many of you don't know root locus? So how do you know Bode Plots but you don't know root locus? Because this is in the same course usually, right? Is it?
It's related to the Nyquist plot.
Nyquist is a little bit more advanced, but you know, usually is a root Lucas. I'm not sure what syllabus they cover in the control, but when we had the control, we usually start with the system block diagram, how you put it together, how you calculate the transfer function, and those kind of things. And the next thing was the root Lucas. And after that was the Bode Plots. And after that was the Nyquist, you know, stability. And after that was the Nichols, you know, stability and those kind of things. But that's good. You guys know at least the Bode Plot. Forget the root Lucas. You know, for those ones they know the root Lucas. For those ones they know. Root Lucas, if you draw the system characteristic, for example, you see something like this. I don't know, let's say a complicated one. And usually this one is symmetrical. These are the pole of the system. These are the pole of the system. See, that's very important. See, this is a j omega axis. See, these are the control theory we are talking about. This is a j omega axis. Usually there is a one k parameter in the system. K parameter, this is the one you are going to select to define, to design your system. For example, if you go very high k, you are going to have a two pole. For example, here, let's say k is 10, for example. You're going to have like this. And for example, this one is going to end up here, for example. These two poles, they are good. Because they are on the left side of the j omega axis. These two, they're bad. These two, they're going to make the system unstable. So you should go select your k. Let's keep it here, right? And maybe two poles here. Now I have these four poles. All of them, they are on the left side, right? So this is another thing. I don't want to go in the detail of control theory. We are not going to talk about the root Lucas. But you guys, for the part 3 of the project, you design the system for critical damping. Don't forget that one. For critical damping. You can start with a time constant of 1 millisecond. That's a pretty good number, you know. Use that one for your control, you know, the KP you have, 1 millisecond. But for those ones, they are more advanced in the control theory. There is a nonlinear control, there is a fuzzy control, there is an adaptive control. There are lots of type of control you can use, you know. But one simple one is this one. You know, you use the Bode Plot. Most of the power supply is used based on this one. They use this Bode Plot things and they design the control system. So, a quickie. We review the Bode Plot, what's the Bode Plot, and we say what's the phase margin, right? And we say to have a good system, stability-wise. We want to have a phase margin of 45 to 60 degrees, something like that. So you learn this one as a rule, you know, 45 to 60 degrees. But you can go read the control books. You see, all of them they mention something with a 45. The higher phase margin, the better, but it's very difficult to get more than 60 degrees. You know, the parameters are going to get unrealistic. You know, but 40 to 50, 40 to 60 is a good number.
So when we have phase margin about, let's say, 45 degrees, we still have like about 30% overshoot.
You have still, your system is not completely unstable, but you are getting closer to this axis. You know what I'm saying? Do you want to be here or here? So definitely you want to be as far as you can from this axis, right? Right? If there is a bomb here, you want to be, you can be 200 meters far from the bomb, nothing is going to happen. Nothing is going to happen. Your ear is going to ring for maybe 1 month, right? When you do that, you know. But if you are 1 kilometer away from the bomb, so the effect is going to be much less, right? So this is exactly what's happening in the system. Every stable system can get unstable. How? You put a big, huge input. You know what I'm saying? When the input is or error signal, something, it's going to make your system unstable. So what's the difference with a good system and bad system? A bad system with a tiny change is going to get unstable. Look at this system again. This is an example we say. If you have a ball here, somehow you fix it here. As soon as there is something here, small force, right? This one is going to drop, right? But how about this system? Shoot this ball. Let's say this one is really high. You're going to go up here, right? The wall is going to go, a few oscillation is going to stay here, right? It's a very good system. All the time it's stable, right? It's going to come back to this point. But this one, as soon as you touch it, boom, the wall is gone. Yeah? It's not the concept of, you know, a stable system and an unstable system. It's just, I'm telling you. So, the further you're from this axis, the better. But you have a limitation. You know, sometimes you cannot go over. 45 to 60 is a good number. for a system. Still, you may do something crazy, something crazy can happen to the system, and the system get unstable. At this point, you have protection in your system. For example, with the inverter design we do all these kind of things. But when you have a huge change, your protection system should come in because your system is going to get unstable. For example, if you have a boost converter, the current is going to start to go up, right? This point was designed for 100 amps. Now something crazy happened, the current will start to go out of range. 120, 140. If you limit, it's going to go to, for example, 1,000 amps. But 1,000 amps is going to kill all your circuit. You have protection. You say, hey, 150 amps is the max you can go. If your control system cannot control you, I'm going to shut you down, right? This is like a kid, If their parents, they can control them, good. If they cannot, at some point, somebody else is going to come in, and shut them down, right? That's the control system. That's the control system, right? No, really, I'm saying this is an example, This is the parents, they are a control system. The kid is the plan. Now, a police, for example, is the protection, right? If this kid is going to go crazy, and the parents, they cannot control him, so someone else is going to step in, right? That's exactly the control system. When the control system cannot control the system, the protection is the police in the system, Hey, you're going too far. If you go more than this much, you're going to hurt all the IGBTs, all the capacitors, everything in the system. Shut down, right? So my point is, even with 45, 60 degrees, yes, maybe your system gets unstable. That's fine. But that one is going to happen very, very rarely. You know what I'm saying? It's not going to happen any minute. You know what I'm saying? You should have a really huge change in your system, in your input. I don't know, there's a tornado, for example, look at the wind turbines, right? The wind is the input to the system. If wind is normal and you have a good system, so the system is going to work. But think about it, if there's a tornado. We didn't design this one to work with tornado, right? So the system, the parameters are going to go out of control. The protection system is going to come in, shut down the inverter, and they're going to have a mechanical brakes to stop the turbine, to lock the turbine, to not let it to rotate, right? Because if they let it rotate, it's going to collapse. There is a limitation on how fast they can rotate. Every system has a protection, and the protection will come in when the control system cannot control the system. So as a rule, we use a 45 to 60 degree phase mark. Because I'm trying to give you kind of feeling about the control system, what we are doing, I mean, even you are the best control engineer in the world, and you design the best control system, still that one can get unstable based on what input you have. But that input should be very crazy input to make your system unstable. And it may still happen. You don't know. When you put it in the field, you don't know what's going to happen. It may still happen. With that point, your protection is going to shut it down, and you're going to restart your system, and you're going to be. Maybe it happens once a year. I don't know, twice a year. That's fine. You shut it down for 5 minutes and you bring it back, right? So that's not a big deal to do that. You see, all the things we have at home, there's a reset button, right? If something happened, it's shut down, and you push the reset button, it's going to start again, right? So. Now let's go back to this guy. We're going to go focus on this. As I mentioned, we said we want to have a high gain at what? High gain at low frequency, right? High gain at, look at it here, if this one has a high gain. What is going to happen? This is the error, right? It's going to magnify this error, right? Basically, your control is going to take a better action on this error, right? If it's a tiny error, right? You're not going to see anything. Tiny things here. You're not going to see anything here. No change. But this one, if it's magnified, not a lot. If you magnify it a lot, it's going to make your system unstable. But if you have a good gain, this error is going to be it will be seen very well in the system, control system, and it's going to react to it, to control that error, to push that error toward the zero. High gain is going to help us to get a zero error. Never ever you're going to get a zero error, but you're going to get very close to the zero error. You know what I'm saying? No control system is going to give you zero error, but you're going to go very, very close toward the zero error. You know what I'm saying? So if you want 100 volt here, right? Look at all the power supply go to the left. just magnitude. Once you are there, use the scope to zoom in on the voltage waveform, right? You put, for example, 10 volt. Go look at it, it's not 10 volt. There's going to be something around 10 volt, right? Always there is an error. But if that error is 1%, based on the application, you know what I'm saying? If it's 1%, maybe it's perfect. Now, for what you're doing in the lab, 1% is perfect. If you have a 10 volt, and now 1% is how much? Is 0.1, right? Is that 0.1? So if you see 9.9 or 10.1, I think for what you're doing in the lab is perfect. It's not going to cause you any problem, right? So my point is never ever this error is going to go to 0, but we want to suppress it as much as we can, right? Bring it as much as close to the 0 error. So the high gain at low frequency is going to help us. Here in the high frequencies, I don't want it. Why? Because we don't want to see those high frequency things in the output, right? We're going to get rid of them. This is just a filter. Look at the 60 Hertz system, right? The inverter you're controlling. So you want to have a high gain in 60 Hertz because 60 Hertz is like a DC for you, right? That's what you're working with. But do you want to see like I don't know, when you are simulating your circuit, do you want to see lots of, 100 kilohertz in your waveform? No, you want to get rid of those ones, right? You want to filter those things, You do some of them with the inductor, those kind of things. Some of it you can do with your controller to get rid of some of those high frequency, components in your output voltage or your output current, right? So we want a high gain in the low, let's say high DC gain, low high frequency gain, right? These are the two things, two of the things we'll keep in mind. Before we go ahead, I need to say something. You need to have a presentation for your 4 phases you did, right? Which day is the final exam? Is it Thursday? Yeah. So, and the final day of the exam is Friday, right? Yeah. Friday is the final day. Does anybody have a Friday exam? So we'll do it this way. Saturday, the first Saturday after the final week of exam, we'll reserve a room here, and every group has 10 or maximum 15 minutes to present all 4 phases. You know what I'm saying? I want you to have maximum 12 to 15 pages, slides for your presentation, maximum. When you present it, all of you should talk. When you are talking, I don't want one person present everything, one person present everything. I want it like a teamwork, If you are 3 members, all 3, for example, one person talk about slide 1, one person talk about, for example, slide 3, one person talk about the slide 4 and 5. I want you to kind of switch professionally. This is like an interview. You are coming over there, and I'm going to ask you questions when you are doing those kind of things. Question. If I feel, for example, he is good in the group, I'm going to ask him. If I think he's not good, I'm going to ask him the question. You know what I'm saying? I'll give you priority. Priority with me. Who is going to answer the question first? If he answered, done. We'll go to the next question. Now I'm going to ask him a question. He passed. But if he doesn't, I'm going to go, hey, what do you think about this question, right? Everybody is welcome to come sit over there. Hopefully some of you will come sit, and look at the other guy's presentation. You can ask questions, if you want, it will be good. It's like a conference. You go present the paper, and people they ask questions, and you have to answer it. But this one, keep in mind, the first Saturday. Yeah, Saturday. I'll play 10 Saturday morning. I need to make sure So we'll put it after. It's gonna be after 10. Maybe we start like 11 to 3. Hopefully we'll finish it in 4 hours.
I don't think we can do Saturday because we have to move out on Saturday until.
So we can do it Saturday before the final exam. I like that one better.
Yeah.
That one I like it better because for me also it's better because I get rid of all the. So I'll ask Arnold to find a room for us, And I don't know how many groups we have. How many groups we have? 11 groups. Let's say the last year went much more than that, but I'm going to keep it this time real short. Let's say 20 minutes with all the question and everything per group. 11 groups is 200 minutes. Is it 3 hours? No, 4 hours. Yeah, we'll start around 11 and hopefully we'll finish by 3. We'll finish by 3. Yeah.
Does that mean like the midterm will be on the final time, like on Thursday?
Yeah. The next Thursday after that Saturday will be final. So you guys, you finish everything in the week 10. You give me all your final report will be due to the presentation time. You know, you can bring it there, and you will have your presentation for the the Saturday before the final exam day. And as I said, keep it, you know, be ready, you know, because I'm gonna just pick on you, you know, make you a little bit, you know, I'm going to a little bit challenge you in the question I'm asking, you know. So that's what I was going to talk to you, you know. How many of you have a problem if you will have the exam in the last session of the class? I mean, Thursday is the last session of the class, right? 3 weeks later, 2 weeks, the week 7, right? Yeah, 3 weeks later. How many of you have problem to have an exam in the last session of the class? You know what I'm saying? The last session is going to be when? I don't know, June, I think, June something. June 4th.
So phase 3 is due next week, and then phase 4 will be due.
The presentation.
Okay.
Presentation. How many of you have problem with the last day of the class? Take the exam of the class. Anybody? I don't know. We look at 3 weeks from now. Thursday, which day? We think about that, guys. Check that. Check the last day of the class. Check the last day of class. You don't have to answer it now. If everybody is good with that,
it's June 4th.
June 4th. So, if everybody is okay with that, we may take the exam that week, and you don't have to come for the final. That is gonna help you a little bit. And I think we're in good shape to finish the material. So.
And 2 days later, minor.
Yes, Thursday will be the final exam. Saturday will be the presentation. Yeah. Yeah. If you don't mind, we'll go to the regular exam. You know, I don't have any problem with that. We'll go with the regular exam time. You know, up to you guys. You know, think about it. If even 1 or 2 they are disagree, you know, we're okay. We are not gonna go. And I would like to take you for a tour to the UCSP Mockingbird at least. Let me talk to Bill Torrey. He's extremely busy. I'll send him an email to see if I can have a tour. But at least 10 of you should show up. At least 10. I want a commitment of 10. You know. Because last time, his time is very valuable. I don't want to bring him over there, 2 people show up, you know. Myself, I have been there 10 times. And really, I don't want to see it anymore. But I want at least commitment of 10 people to come. If there is no 10, I'm not going to set it up. Because I cannot bring you that much, and it's kind of a little bit, you know, embarrassing. And nobody shows up, you know.
When is it going to be?
Who is based on his schedule, you know. I'll tell him to give me your time when you are available, you know, and I'll give that time to you guys, you know. So if we can find 10, well, perfect. If it's not, I'll tell him with the motion, you know, we'll not go. Because I have to go with his schedule, you know, and to see when he's available. I'll try to put it early morning, like 8 a.m. One of these days, you know. Yeah, and 8 a.m. is not early, you know, just to let you know. I wake up every day like 5:30, you know, but I'm saying 8 a.m. You know, just to start and finish maybe 2 hours, and then you go. Any questions? So let's go back to what we were talking. Now we are going to focus on the compensator. Or error amplifier. So when we design the transfer function of this compensator, what we want a high DC gain, low high frequency. This is one. Now, coming back here, this is a TC, this is a TM, this is a TP, right? So, I'll define T open loop. The reason I'm saying open loop, I'll say TC times TM times TP. Basically, if you look at this system, it's going to be like this. Vref, VO, TOL. Open loop means just get rid of this loop, right? That's what they call it TOL, T open loop, right? If you didn't have a feedback in the system, this one was the transfer function of the system, right? Open loop, open this loop. What's the transfer function of the system? Right? What's the transfer function of closed loop system?
The
Is
forward
this
path.
divided by 1 plus this, right? Because the gain here is 1, right? So, we said, I want to see how to write it down. Crossover frequency of the TOL. Let's say, let's do this. TOL, how should I write it? I want to say crossover frequency of TOL. What does it mean? When TOL is going to become 0, right? When we have a TOL, this is a, for example, let's say this is the TOL, 20 logarithm of the TOL, right? Crossover of TOL is this, frequency of TOL is this frequency, right? We want this frequency to be as high as possible, as high as possible.
Unity gain frequency.
Huh?
That's what we call it in unity gain frequency.
Unity gain frequency, yes, at the high frequency. This one is going to kind of, you know, if this crossover frequency is high, and we say the gain is 0 or unity, if you look at it, not decimal. So it means the high frequency gain is low, right? We want this crossover frequency as high as possible, but much smaller than, at least in 1 order of magnitude, less than the switching frequency. For example, let's say the switching frequency is 100 kilohertz. What number do you set?
10 kilohertz.
10 kilohertz, right? So this number is not a rule of God, you know, to say it's going to work every time, but that's a very good start, you know. All this control system, usually you start with some number, you know, some good guess, and you go look at your performance, and you're going to change. You should come to the company I'm working, you know, I come up with some KPKI, we'll put in the control system, and hopefully we'll get something. And we start to change it, like, let's okay, change KP this much. Not blindly, you know, there is a point behind it, you know, how to change it, you know. But we start to change this thing, let's bring the KPKI a little bit more, or less, you know, those kind of things, you know what I'm saying? We start to look at this to see when we're going to get the best performance of this system. Because this system, at the end of the day, they are very nonlinear. See, the inductor we put here is not as simple as L, you know. When the current changes, the inductor value is going to change. When the current change, voltage change, the capacitor value is going to change. The R value in the system is going to change. You know, all those kind. We do the best we can to model this system, get some good numbers, right? And now we try to put in the real system to do the, we call it fine tuning, you know. So here, we want to have this omega cross as high as possible, but very far from the, at least an order of magnitude less than the switching frequency.
Why do we want to design as possible?
See, what's happening in that omega cross? How much is the gain?
0.
0. So it's going to kind of guarantee this part, right? Right?
But wouldn't we want it lower?
No, I'm saying, see, that's good. It's going to be 1. If you go high, lower is better. You know what I'm saying? It's as high as possible. You know, we're going to go with this rule. You know, but if the switching frequency is 10 kilohertz, right? So we go with the 1/10 of the 1 kilohertz, right? We don't want to see anything more than 1 kilohertz in the waveform. You know what I'm saying? You want to get rid of the effect of switching frequency in your measurements and everything, you know. When you design a filter, you know, lots of time when you sense the current and voltage in the power converter, you need to design a simple filter. to kind of clean up the waveform. Usually, the corner frequency of that filter, you can select 1/10 of the switching frequency, 1/5 or 1/20. You know, these numbers is how, because any filter you put in the system, what's the problem with the filter? And so we tell me what's the problem with the filter? See, I have this current, for example. Let's say this is the output inverter. When you simulate your inverter, you're going to see this is what you have. Right? I need to sense the current, bring it to my DSP, right? And usually I filter this current, right? When I filter this current, this ripple, you know, based on what corner frequency I'm selecting, right? I'm going to clean up this waveform. That's the name is filter, right? It's going to clear up this signal. What's the problem with this filter?
You must have pressed on original signal.
Huh?
You must have pressed on original signal.
So that one I can define the gate to make sure we're going to get the right one. There's a bigger effect. Every filter you can look at it as a complex number, right? Let's say the gain kind of designed to be 1, right? There is some angle here, right? So the signal is going to, just I'm exaggerating it here. The signal is going to be like, this is a filter signal. Okay?
There's gonna be a little lag.
Reduce the phase margin.
It's going to affect the phase margin. But the problem here is, this is not the real signal I have in my system, right? I cleaned up my signal, it's better now, but it's shifted. Believe me, this one is causing us lots of problems. The PLL we have, you know, the PLL, until you fake it, you know, what we have in the company, because we have to clean up this signal, right? We have a filter to clean up this signal. We have to add, we call it fudge factor. We have found it out by experience. See, this one is about 3 degrees. You know what I'm saying? We are adding, whatever we are calculating, we are subtracting, we are bringing 3 degrees ahead. You know what I'm saying? With the -3. We add that one to bring it here. The problem is, this is not fixed for all the currents. It's going to be different. You know, for example, 10 amps is here, 4 amps is here, I don't know, 5 amps is here. The problem is that, but this one, once I should bring it, I have a paper I can show you, you know, it's from another, not me, from somebody else. This little thing, it's causing lots of problems. They call it zero cross effect. They call it zero cross effect, you know. When you cannot find the zero cross accurately, it's going to cause a problem in the current waveform. If you look at the current waveform, it's going to be like this. Okay, here, let's say for unity power factor. You're expecting to see something like this, right? You're expecting to see something like this, right? What is going to happen, because you're wrong, you have some error. What you're going to see is something like this. You're going to see something like this here. The one is happening because the PLL from here is going to go like this, right? In this one, it's not going to happen. But as soon as here, every cycle, so here again is something like this and it go like this. And this guy, they have to do a PhD. PhD is a big problem. Yeah.
Can't you pick an inductor and capacitor so the phases cancel?
You cannot. Believe me, we have spent a lot of time on it.
Okay.
It took a lot, you know, we tried a lot to do that, you know, because this is dynamic, it's not fixed. If it was one value, you're right. You go find that one and compensate for that, you know. But this one, for different current, different voltage is different. Voltage is fixed, fortunately, is 120 volts. But the load is variable. You know, the load is variable, is going to affect this one, you know. We spent lots of time on this, but now it's better. It's much better than what it was before, you know, but it still is not what you want. For example, the CEC standard. See, there are lots of pulleys around here. You know, they're not going to let you go do whatever you want. CEC has a THD profile. I want to finish this thing, you know. I'm talking too much, but this CEC standard. When you design a solar converter, let's say 5 kilowatt converter, right? You know what's THD, total harmonic distortion for the current, right? They have a rule, very, very strict rule, you know, but I'll tell you a very simple one. It says at 1/3 of the rated power, you should be still less than 5%. What I'm saying, because when the power goes up, this one is going to get better and better, you know. Because look at here, you see the same thing, but the bigger current is here. You know what I'm saying? Yes, you have this effect. Well, look at it. Overall, the fundamental is much bigger, right? It's going to help you with the THD, you know, the a few examples we solved. When the power goes up, it's going to help you with THD. When you have this one, the THD will be like 3%, 3.2%, right? But when your current is low, look at here, you have the same effect. Instead of having this much fundamental, you have this much. This one is going to show up more in the THD. Now, fortunately, we have solved it with the 5 kilowatt we are working. This one is going to be on the market, you know, in Europe and here. We have 4.5% for this one, but now this is a one number I told you. Now it said the third harmonics, the fifth harmonic, they have a limitation. Even harmonics, all those things is going to be there. Right now we have a problem with the high frequency harmonics. We have some around, I don't know, around maybe 100,000 hertz, something like that. You see here, they are more than what is limited, you know, is allowed. You know, the overall THD is less than 5%. We are good. We are 4.5 for this one, for 1/3. For the full rating, I think we are like 3.2%. You know, but with this one, still the second harmonics in the system is high, and some higher order frequencies. They are more than what is the limit. They give you a specific table. When you design this thing, they're going to test your inverter to put that standard on your inverter box. And I'm going to let it go. You know what I'm saying? We have to go through all this. Yeah.
So did you find a way to reduce that?
We're working on it. We're working on it. You know, if you know with all the answers we've done here.
Why don't they just use a digital filter?
We do, believe me, we do lots of digital filter, but this thing is going to be this delay, whatever filter. See, the difference between digital filter and the analog filter. Analog filter, you build it with the parts. Digital filter, you build the transfer function, right? Both of them, they have a delay, right? That if you look at it mathematical wise, they're the same thing, right? This one has a transfer function. You build it in your DSP just with a, I don't know, programming, right? The analog filter, you build it with the RC elements, right? RLC elements, right? So basically, both of them still, they have one transfer function at the end of the day. And that one is very popular. Yeah, we're doing a lot of work on this thing. It's getting better, but not still there. And we're very close. We're very close to work. It's like they paid us $1.2 million to do this project. You know, it takes time. You know, 3-4 people there at least working on it. You know. Okay, let me finish this thing. You know, because any question anymore? So we said, let me put it here. So this is a crossover frequency, right? When the TOL, the 20 logarithm of TOL is 0, we want omega cross as high as possible. But one order of magnitude less than, you can write one order of magnitude less than omega s, let's say omega SW, switching factor frequency. So 1/10, or you can put the omega cross simply, put it omega switching over 1/10. You know, put it here. Right? FSW is the switching frequency. We want to have a phase margin of these are what we follow. These are the basic rules to follow this. We want to have a phase margin of 45 to 60 degrees for the system. Now, keep this three in mind because we're going to continue this one next Tuesday. I want to start with this one. I'm not going to apply anything here. First, I want to start with this one. Let's look at this system. We call it error amplifier, right? We call it error amplifier. You know, there's a company, how many of you know Ametec? Ametec is a local company here in Toronto Valley. They design lots of high power supplies, solar simulator, lots of good things, you know. And they are pretty old-fashioned thing, old-fashioned company, you know. They use all analog. Analog is very good, you know, a very high bandwidth, you know, system. But now they're asking one of the things we are doing, we are kind of modifying all the power supply this thing with the DSP. We are making it digital. What they have right now in their system is this kind of controller. I'm going to put it here. They build it with the analog parts. But what I'm doing here, we're not going to talk about that. You can do that one with the digital. That's like a PI controller. I told you the inverter. The PI controller easily can build it inside the DSP, right? You don't have to build the circuit, you know, RC circuit with the PI. If you go 20, 25 years, 30 years ago, they used to that. You know, the PI, they will find the kind of analog circuit is going to work like a PI, right? But if we have a system, not system, we have a circuit like this. Let's call this one ZI. And VF. And this is the VREF. And this is the VO. This is basically what we have in the error amplifier, right? VREF somehow minus. What's the transfer function here?
Just negative VF.
Yeah. Basically, so the transfer function is going to be for now. Let's put it this way. Let's make this one easier. Put this one here and put this one. Make this one VI and this is VO. The transfer function VO over VI is minus ZF over ZI, right? You know this one, right? From the circuit theory, I think we have done this one many times. You know. So this is a transfer function for this system. Now, this one they call it type 2, I'm thinking about should I write it down? Type 2 compensator. I'll put it this way. Type 2 compensator circuit. As I said, I'm not going to talk about the control right now. Just I want to find the transfer function of this system to see what it is, and I'm going to use it in the next class. Tuesday we may stay like 30 minutes more, you know, to cover up for the class I was not here. So if you look at it, this is ZI, right? And this is ZF, right? Let's say ZF. How much is the ZFS? It's going to be this one parallel with this one, right? 1 over C2S parallel with R2 plus 1 over C1S, right? That's Z to ZF. And how much is the ZI? 1 parallel. So VOS over VIS is going to be, let's use this one, it's going to be this one times this divided by this one plus this, right? So it's going to be minus 1 over C2S times R2 plus 1 over C1s divided by 1 over C2s plus divided by R1. So you will calculate this transfer function, but to let you know later on, which we are going to talk about in next class, I want to select this R1, R2, C1, C2 such that it's going to satisfy those conditions I put here: high gain, phase margin, all those kind of things. We're going to leave it for that class. But right now, let's first of all find this transfer function. You can use the PI controller if you want. You don't have to use it. But this is the one proven circuit. It has worked very well in the industry. That's the reason we are using it now. But if you are going to come up with, there is a type 3 compensator. There are different type of compensator. This is one type you are talking about. Now, if you do the calculation here, it's going to be R2 C1s plus 1 divided by, I'm timing this one, C1 C2 s squared divided. And this one is going to come to the denominator. R1 times R2 plus 1 over C2 plus 1 over C1 times 1 over S. Right? So let's time it by this, R1, C1, C2, S2, right? So it's going to be R2, C1 plus 1 divided by. So we're going to time it by this. If we time it by this value, so it's going to be R1 times R2, C1, C2, S squared. So this part times this, right? Now this one times this. One of the S is going to cancel, right? One of the S is going to cancel. C1, C2 times this one is going to C1. C1, C2 times this one is going to C2, right? Basically, it's going to be, right? So let me make this a little bit. Oh, there's a minus. This one minus somewhere. There's a minus here. So I want to write it this way. I'm missing one S here. Right. I want to write it this way. S plus 1 over R2 C1, right? I want to write it this form. I'm factoring R2 C1 here, right? So there is a R2 C1 here. R2 C1 here. So let's divide the denominator also by the same thing. So it's going to be 1 over minus 1 over R2 C1 times. Here, I'm going to have S times, I'm factoring S, is going to be R1, R2, C1, C2, S plus C1 plus C2. Right? But still, I want to make this one a little bit more meaningful. Yeah, I want to have it as well. Let's factor this one again. If I factor it again here, so VO over VI is going to be, I should factor this one, right? How much is going to be? It's going to be R2 squared, right? C1 squared, right? R1 C2 times S plus 1 over R2 C1, and this is going to be S plus this one divided by this is going to be 1 over, let's put this C1 plus C2 over R1 plus times R2 C1C. Right? That's the transfer function. Did I read it correctly?
The R1, we multiply with C1 and C2 on top.
Here? This has factored this part, right?
In the previous, on below, you have R1 on the outside.
Oh, yeah, you're right. Yeah, you're right. There's the R1. Right? Hopefully I'm right. Yes, that's right. Now, let's compare this one. Keep this one in mind. I'm going to put another transfer function here. Look at this one. If you have a system like this, not a system, just keep this one here. Let's call this one omega z. Because that z is a 0. I will put a z for 0 is the numerator. And this one called omega p. Right? So if C1 is very, very bigger than C2, this is what we are doing within the design when we are going to do that. How much is omega p? If C1 is very, very bigger than C2, this one is gone, right? Right. 1 over R to C2, right? So omega z is 1 over R to C1, omega 2 is 1 over R to C2. Why did I write it this way? Because now if you look at this one, this is a gain, let's say A over S times S plus omega z S plus omega p, right? It's like this. It has a one pole at what? 0. One pole, 1, 0 at omega z, and one pole at omega p. Which one is bigger between these two? Omega p is much bigger because we said C1 is very, very bigger than the C2, right? If you look at the transfer function here, it's going to be like this. Let's call it H. Basically, it's going to be like the one I put in here, right? What is this? This is omega z. What is this? This is omega p, right? Let's look at the phase. Let's look at the phase. The phase is going to be, we are going to start with let's say if these two they cancel each other. Very easy way to look at it. If these two they cancel each other, how much is the phase all the time? Minus 90, right? You start from minus 90. Right? When we go to the infinity, what is going to happen? These two they're going to go away, right? These two again they're going to cancel each other. It's going to be again in infinity also they're going to end up minus 90, right? But here, I'm going to talk a little bit more about this in our next class because we don't have time. You can see this one is stronger than this one. You know, when we go from here, and let's call this one boost, and we're going to stop here. Basically, the crossover frequency is here. Remember, this is omega cross. So this is a Bode plot of a type 2 compensator. Keep this one in mind. Now we know what's the transfer function for this guy, right? We know this one, we know this one. But I need to select the parameter to satisfy what I put here as a design criteria, right? That one we need to work on. In the next class, we'll go through and we'll do one example after that. And we'll be done with this.